shortest path problem. Shortest path problem. All right, so what basically is this shortest path problem is? Okay, there are several paths possible from going from one vertex to another vertex in a weighted graph. Okay, in a weighted graph, from any one vertex, from one point to any vertex, it is, but there are several possible paths. But the shortest path, okay, the shortest part is the part in which the sum of the weights of the included edges is the minimum. All right, suppose if I consider a graph like this, a directed graph. Let me take one directed graph here. All right, this is a directed graph. 0 1, say 4, this is say 3, this is 2, this is say 5, and this is 6. All right, and let me, this one is 7. Okay, no problem, 7. All right, so you can see this is some extra only, then join this. All right, this is the graph, I guess. Yes. So let me take this a directed graph. You can see that, suppose if we have to go, so this is the distance 9, this is 2, this is say 6, 4, and this is 2, this is 10, this is 4, this is a 6, this is 5, and this is 3, and this is somewhat 3. All right, suppose if we have to go from vertex 0 to vertex 4. All right, so if we have to go from vertex 0 to vertex 4, so we can take the part like from 0 to 2, okay, from 0 to 2, and 2 to 3, then 3 to 4, and the length of this part would be 16. Okay, 3 plus 10 plus 6, 3 is 16. Now, but this is not only the part from vertex 0 to vertex 4. There are other parts which may be shorter. Okay, which may be shorter. So we are interested in finding the shortest of this part. Okay, the other two parts can be, so from vertex 0 to vertex 4, right? So what are the parts? Part was 0, 2, and 3, and 4. So the total sum is that would be 16. Next the other part is from 0 we can go, from then 2 we can go, okay, and then 5. Yes, for that we need to go to like this, so we can go from 0 to 2, then 2 to 5, yes, 2 to 5, and then we can go from the 3, and then we can go 4, and the length of this part will be 12. Right, this is one another way. Next, another part will be like this, from 0 to 1, and from 1 to 4, that is for 11. So you can see that I have taken find out 3 possible parts, and the shortest part is from 0 to 1 to 4. So this is not necessary that the shortest part is unique. The shortest part is unique. All right, so we are going to study one algorithms for finding the shortest part, that is called as your Dijkstra algorithm. So what is Dijkstra algorithm is all about? All right, so this Dijkstra algorithm is named after E.W. Dijkstra. This is spelled Dijkstra, Dijkstra, who gave this technique of finding the shortest part. Okay, in the year, it may be 19 in the year 1950 something, 1950 to 19, so it may be around 1950 to 1960. Within this year, I think I have not remembered much. So what actually going to do is that in this algorithm, so we are going to find the shortest path from the source vertex to all other vertex in the graph. And then this type of algorithm works only correctly only if the weights of the graph are non-negative. So let's understand what is directed graph, what is a Dijkstra algorithm is all about. So suppose if we have provided with a graph of a nodes where every node is linked to several other nodes with varying distance. Okay, now what will you do? You begin from one nodes. So this is one example. So what you do, we begin from one nodes in the graph, and what is the shortest part to other part in the graph. All right, so we know that an algorithm that is used for finding the shortest path from starting node to target node in a weighted graph is known as your Dijkstra algorithm. Okay, so this algorithm makes a tree of the shortest path from the starting node, that is your source node, to all other points in your graph. Okay, so this Dijkstra algorithm makes uses of weights of the edges for finding the part that minimizes total distance, that means total weight. Okay, that means distance weight among the source node and all other nodes of vertices. All right, from one nodes to from all other vertices. Now, so this algorithm is also known as single source shortest path program. Single source shortest path algorithm. All right, so this actually it is also an iterative programming or algorithmic process. That means the process is going to be repeated. Okay, repeated again and again until we find the shortest distance. So let us understand how can we implement this Dijkstra algorithm. So let us before we implement this Dijkstra algorithms, let us understand some of the essential characteristics of a some of the characteristics of Dijkstra algorithms. So how it going to works? Okay, so basically these algorithms actually begin from the nodes to be selected. Okay, first we have to select the source. So we have to select the source node, and it examines the entire graph to determine the shortest path among that node and all the other nodes. And what we are going to do, and we are going to examine the entire graph. Okay, so we have entire graph to determine the shortest path, to determine the shortest path among all other nodes. Now this algorithms, second one is this algorithms maintain the track of the currently recognized distance from each node to the source of this to the source code, and updates it these values. All right, so and this it maintains the track of the currently recognized shortest distance from each node to the source code, from each node to the source code. All right, now and updates its value, and updates, and this updation is called as your relaxation. Okay, updates this values, and updates its values if it identifies another shortest path. And the third point says that once the algorithm has determined the shortest path and admit the source code to another node, then the node is marked as visited and can be added to the path. Okay, and then once determine the shortest path admit the source code to another node, the node is visited, the node is marked as visited and can be added to the path. And the fourth says that this process is going to be continued till all the nodes in the graph have been added to the path. Okay, so process is going to be continue till all the nodes have been added where to the path. So as this way a path get created that connects the source node to the other parts. Okay, and we can get the from the that means a path gets created that connects the source node to all other nodes following the possible shortest path to reach each node. So this is one characteristics of a Dijkstra algorithm. In the Dijkstra algorithm implementations, what we have to do is that the very first step is to we have to mark all the nodes as unvisited. Okay, we have to, suppose if we have a graph and that marks, we have to mark all nodes as unvisited. And the second thing is after then we mark the pick starting node with a current distance at 0 and other rest of the nodes with infinity. Suppose if we have a graph like this, suppose if we have a graph like this, All right, suppose we have a graph like this. Suppose and 0 is my source starting nodes. So in the very first step, what as I told you, all the nodes have been marked as unvisited. Then we have to select the starting node and mark as your, and so this is my starting nodes, and then with a distance of 0. So distance is has marked as 0, and the rest of the as infinity, because we don't know the distance, so we mark as infinity. This is what it means. And then now what we have to do now, fix the starting node as your current node. So I'm going to fix this is my starting node, right? So this will be my the current node. So for the current node, analyze all its unvisited neighbors. So we have to see the unvisited neighbors. So from 1 and 2 unvisited neighbors, and measure the distance by adding the current distance of the current node to all the weight of the edges that connects the neighboring nodes and the current node. And the fifth says that compare the recently measured distance with the current distance assigned to the neighboring nodes and make it as the current distance and the distance of the neighboring node. And after that, consider all of the unvisited neighbors of the current node, mark the current node as visited. And then if the destination, from here to it wants to reach here, if the destination node has been marked visited, then stop and algorithm has ended. And else, choose the unvisited node that is marked with the least distance fixed it as the new current node, and repeat the process again. Okay, so this Dijkstra algorithms, okay, what is that Dijkstra algorithms? I'm going to explain. Okay, suppose if we suppose this is my graph. Suppose this is my graph. So this is one graph. It's from A, B, D and C. Okay, and then I put the distance 2 to 4. So this is say, let's say 3, right? So if I select A as the shortest distance, A as the shortest part, and if I want to go to D, if I want to go to D, there is a direct path from B, but there is not a direct path from A to D. Okay, it can go through B only, right? Now, so what we have to do, we have to find the shortest path from B as well as D. Okay, so if we see the graph, then there is a direct path from B only. So and you can see it course is from A to B is 2, and there is no direct path to D, right? What it means that if I want to travel from A to D, because A is a starting node, there is not a direct path from A to D, but it can be traveled through via B only. And the distance from A to B is, say, suppose it is 2. Okay, we don't know what is, and because the distance from here is 2, but we don't know the distance from A to B is, so we mark as infinity. So we mark as infinity. From here A to B is 2. All right, now in the case of a Dijkstra algorithms, what A is A select the shortest path, and once you select the shortest path, and once we select the shortest path, then check via that vertex. We have to check from this vertex, that vertex is there. Okay, so via that vertex is there shortest vertex to any other vertex. From B, is there any shortest vertex to reach to D? Okay, so let's check again. So A will select the shortest path from this shortest path to any other vertex. So this so Dijkstra algorithm, what is going to select? It will select the shortest path from the shortest path to any other vertex. So this updation is called as the relaxations. Okay, so as I told you that from the shortest, if I want to reach D, there is not a direct path from A to D, so it can be traveled through B. So once A select the shortest path B, then it will check, it will select the sort and check via this whether from B is there any possible path that can reach D. Okay, the shortest possible path that can reach D. All right, so this is called as this is updation. So this updation is called as your relaxation. This updation is called as a relaxation. So what do you mean by relaxations? Relaxation means from the from starting node, what starting node A is going to see, the shortest part. Okay, so B is selected. So what does B is going to do? So B is going to select, going to check any other vertex which have a shortest part. Okay, that means the vertex has been updated. Okay, so it is going to check, okay, and check via that vertex. Via that vertex means from via that vertex B, is there any shortest vertex to other vertex, that means to D. Okay, so that updation is called as your relaxation. Okay, so suppose if the distance from A to B is 2. All right, if the distance is U, suppose this is my U and this is my V, and how this relaxation works? Relaxation works like this. If distance is distance of U plus cos of UV should be less than distance of V. All right, so what is the distance of U? Distance of U is 2. What is the cos of UV? Cos of UV is 4. Is less than distance of V is what? Infinity. Then d of V is equal to d of U plus cos of UV, and then is equal to 6. So we have to do relaxation for each vertex. So this infinity will change to 6. So this is called as your relaxations, and we have to do relaxation for each vertices. So this is how your Dijkstra algorithm is going to work. So let me take an examples. Okay, let's take an example to find the shortest part. Suppose I'm going to draw a graph. All right, so this is A, this is B, so this is E, this is C, and this is D. Okay, the distance from A to B, see, this is the part 1, 5, 7, this is 5, so this is 2, this is 7, and this is 1. All right, so step 1. What does the step 1 says? During the executions of this algorithm, each node is going to mark with its minimum distance. Okay, so minimum distance to node C. As we selected node C. So minimum distance. What is the minimum distance? So I have selected C as my source node. So the minimum distance that are going to be marked here each 0. Right, it's 0, and the rest of the nodes as infinity, because we don't know the distance. So I mark as infinity. Got it? So now next is, what is that? We have to mark the vertex C with minimum distance is mark distance 0. Got it? We mark distance 0, and the rest of the vertex with infinity, as we accept C, because we don't know the distance. Next, step number 2. Step 2. So this is just step 1, right? Step 1 results. So 1, 2, 3, 4, 5, 6, and then 7. A, B, D, E, D, and C. So this is 0. All right, and the rest will be infinity, infinity, and infinity. 1, 7, 3, 1, 5, 7, 2. All right. Now next, step number 2. In step number 2, what does it says? That means now the neighboring of node C will be checked. What are the neighboring nodes of C will be checked? That is node A and node B, and node and node D, right? So neighboring of C are A, B, and D, right? And we start we start with B. Let's start with B. Here we will add the minimum distance of the current node 0 with the weight of the H, that is 7, that link the node C to node B, and we get 0. So from B, what we get 0 plus the 7, and we get 7. Now this value is going to be compared with the minimum distance of B, that is your infinity. The least value is the one that remains the minimum distance of B. Like in this case, 7 is less than infinity, and mark the least value to node B. So instead of infinity, it will mark as 7. Okay, it will mark as 7. Now, so the answer will be, so your new graph will look like this. So 1, 7, 2, E, B, D, C, A. So 3, right? This is infinity, this is infinity, this is infinity. What about this? It will be changed to 1, 7, and 5. Got it? Now, next step. Step number 3. Step number 3. Now the same process is checked for neighbor A. For A, what we have to do? We add 0 with 0 plus. What is the weight of this from A to C? A to C is 1. So A to C is 1. So we get 1 again. And 1 is compared with the minimum distance of A. What is the minimum distance of A? Till now it is infinity, and it is less than, and mark the lowest value. So the lowest value, then now A will get like this. So this is B, A, C, D, and E. So what is the minimum distance of A? It was infinity, it was cut, and it was in mark. What are the infinity? It is 7, right? So 3, 1, 7, 2, 5, 7, and this is distance 1, right? And this is infinity, and this is also infinity. Got it? Next, the same is repeated with node D. Next, for step number 4, for D, so 0 plus 2, and it is 2. 0 to 2 is 2, right? So it and mark as infinity. So we get the result as like this. A, C, D, B, E. This is 1, this is 7, and this is 2, this is 2, 1, 7, 5, 7, 1, and 3. Got it? And what about this? This is tends to infinity. Now since the neighbors of node C have checked, so node C is marked as visited with the, so node C is marked as visited. So I'm going to highlight it. I'm going to make as here. So C is marked as visited. C is marked as visited. Now we will select the new current node. Next is step number 5. What is the next step? For that we need the current node such that the node must be unvisited with the lowest minimum distance, or the node with the least number or no check mark. Here node A is unvisited and we have minimum distance of 1. Out of this, one distance is 1, right? So I'll select A. So select as minimum distance and mark with as, and mark as A is the, now A is the current node. Now A is the current node. Okay, so A is the current node. Now current node is that. Now we will repeat the algorithms, checking the neighbors of the current node while ignoring the visited. So only, if you see here, only A neighboring node of A is C and B. So C is already visited, so we will select B. Okay, so B is checked. For B, what is the node? We add, what is the node? Distance is 3, right? And what is the distance is 1, and what is the weight? Is 7. 1 plus 3 is actually 4, right? 4. So we obtain 4. The value of this 4 will be compared with the minimum distance of B. What is 7? 4 and 7 will be compared. 4 is less than 7. Yes. So mark the lowest value of lowest value, that is 7, at B. So instead of 7, it will be so it will be 7, right? So it's 7. It will be 4. So your graph will look like this. So B, D, this is E, D, C, A. This is infinity, right? This is 2. This is already visited. This 1 and this is 7, right? So 3, 1, 7, 2, 5, 7, 1. So this will cancel and it will mark as 4, right? It's 4. Now after this, step number 6. Step number 6, after this, node A is marked as visited. So the next is A is visited. A is marked visited. So A is also be highlighted. C is also going to be highlighted. A and B. This is C, and this B, and this is E, and then we have D, and these are visited. All right. Then what we have to do for the next, we have to select the 1, 4, and then infinity, and this is 2. 7, 5, 1, 3, 1, 7, and 2. Now what we have to do, we have to see the distance. Okay, for node E. Okay, for node E we have obtained 2n. So node E we have obtained 2n. What is that? 2n distances from here, node E, right? So for node E, step number 7. In the step number 7, select D as the current node, as D as the current node, right? So what are the distance for B, D and E? D is 4, E is infinity, so we will select B. For B, what is the distance? The distance is 2, and then age from here 2 to 5. 2 plus 5, that is 7. Now compare with the minimum distance 7. So 7 is greater than 4. So leave this distance value at node B as 4 only. Right, at 4 only. There will be no changes. Now for node 3, for node E, right? So infinite here is 2 to 7. 2 plus 7 is equal to 9. And then compare with the minimum distance. 9 is less than infinity. Right? 9 is less than infinity. So mark D as what is that? It will be 9. So instead of alpha infinity, we will mark as 9. So this now D is also visited. So this is 9, this is 4, this is 1, 1, 7, 2, B, this is C, A, right? And then this is 3, 5, 7, 1. So this is visited. Now D is visited. Okay, so the next one. Now as you can see that D is not so the current node is 4. The current node is B, right? So for D in step 8, current node is B. So current node is B. So what we have to check? We have to check from B only E, right? E is unvisited. So for E, what is the distance? 9 plus what is that? It is 9 plus 1. Oh yes, it is 4 plus 1. It is not 9. It is 4 is 1 is 5. So 5 is less than 9. So place in place of this. So 1, 2. So little bit darker shades. This is also B, E, D, C, A, right? So this was 4, this is 1, this is 2, this is also, this was 0, right? And then this is changed to 5. This is changed to 5, and then mark this change, so for the node B, right? For the node B, this is marked, and then so mark as 5. We mark D as a visited node with the green one, and mark E as the current node. Now E is the current node. So now mark B as your current. So mark B is mark, right? So B is mark. Now step number 9. So current node is E. Your current node is E, right? And then what we have to see that since it does not have any unvisited neighbor, so there is no requirement to check in anything. Now E is marked and as a visited node. Okay, so just E is marked as visited, and you get the final answer as like this. This is also visited, this is also visited, this is also visited, this is also visited. C, D, E, B, A. What is the distance of A? It is 1. It was alpha before, it was 1. It was alpha, it was 7, and then it is 4. It was alpha, it is changed to 9, and then it changed to 5, right? And then it was alpha, it changed to 2, it is 0. 1, 3, 7. 1, 3, 7, 2, 5, 7, 1. All right, so we are done with this as no unvisited node is left. So the minimum distance of each now